Here are the identities stated a little again, and I just want to identify what they are for you. The first one is the Pythagorean identity, and it comes from our fact that we know that all of our points were on the unit circle, that the sum of the squares has to equal 1. These next two identities correspond to our sum identities for sine and cosine. And you'll notice I've changed the names of my variables. I'm now calling them any variables I want. So I could call them x plus y, theta plus phi, a plus b. Notice though that the sine has an addition for the two terms, whereas the cosine has subtraction. Second, notice that the sine, when I do the sum identity, involves sine and cosine. So sine times cosine and cosine times sine. Whereas the cosine has both cosines together and both sines together. Okay, so that's how I try to remember what those are. Now, from these, we can actually get a number of consequence identities as well. One of these is what happens with subtraction. And I'm not going to use subtraction a whole lot, but if I do subtract and say what's sine of x minus y, that's the same as adding negative y. And the effect is it changes the plus to a minus in the sum. That's all. On the other hand, if I do cosine of x minus y, it does the same thing. It changes the sign of what happens from a minus to a plus. All right, so that's our difference identities. The second identity that we're going to talk about is something called the double angle formula. So to double an angle means that we take an angle times 2, which is the same as adding it to itself. So we can get the double angle formula by just thinking about the sum identities and saying that we're adding x to itself. So sine of 2x is the same as sine of x plus x. And so now we're going to think about this second x as if it was the y. And so we get sine of x cosine of the other x plus cosine of the first x and sine of the second x. Now these two terms are actually the same, right? What I called the first x and second x didn't really matter. And so my sum identity for the double angle formula is that I get 2 sine x cosine x. If I play the same game with the cosine of the double angle will be cosine of x plus x. And so I get cosine of x times cosine of x, that's cosine squared, minus sine of x times sine of x, and that will be sine squared. And I want to emphasize that when I write this, it means find the cosine and square it and subtract the sine of x squared. So this is really a composition. Okay? All right, so that's the double angle formula. All right, our third identity that often occurs is something called a half angle formula. And it comes from taking our double angle formula for cosine. So let me write that. It comes from saying that the cosine squared of x minus the sine squared of x is always equal to the cosine of 2x. And our Pythagorean identity says we know that the cosine squared of x plus the sine squared of x is always equal to 1. So I have two equations, and if I add the equations together, I end up with 2 cosine squared of x. The sines cancel, and on the other side I get 1 plus the cosine of 2x. And the reason it's called a half angle identity is if I solve for the cosine of x, I get the cosine squared is equal to 1 plus the cosine of 2x all over 2. Okay, so the cosine of x, half of double the angle, is either plus or minus the square root of the sum 1 plus cosine 2x all divided by 2. Now the sine, the only way I can figure that out is by checking which quadrant I should have ended up in. If I subtract instead of add, and I'm going to take plus the second equation and minus the first equation, okay, it's really sloppy notation, but this time the cosines are going to cancel and the sines are going to add. I get 2 sine squared of x equals 1 minus cosine of 2x. And the half-angle identity says if I solve for sine, I'll again get either plus or minus, and then I get a square root of 1 minus the cosine of 2x over 2. Now, in calculus, it's more common to actually leave it in the squared form rather than taking the square root. This often ends up being used in an integration, which is something that shows up in Calc 2, not in Calc 1. All right, so let's summarize where we've been. We previously knew the Pythagorean identity, which came from knowing that we're on a unit circle, that the sum of the square of the x-coordinate and the square of the y-coordinate is always equals 1. Then, from the idea of adding rotations as composing the rotations, we get the sum identities for our angles. And this is what we're going to use when we calculate the derivative of sine and cosine. We'll need to use these identities. Then when we thought about the special case of a double angle, we ended up finding some formulas that will be used in trying to understand how what happens to my coordinates if I ever double my angle. And then we have our half-angle formulas that, as I mentioned earlier, often get used in integration. And the reason they get used in integration is what we end up doing is we say, I might be working with a square of a cosine or the square of a sine, and we can actually rewrite that in terms of something involving twice the angle, because now I've gotten rid of a power and it's a sum instead of a power, and that's going to be a lot easier to work with. All right, so those are the key identities for our trigonometric functions. In another video, we'll look at some examples of how we use them.